Thank you for the invitation. Thank you for the delicious food. Thank you for taking some time out of your Wednesday evening to come and listen tonight. What I'm going to try to tell you about is a very exciting and relatively recent development in which information theory has been successfully and seriously informing our attempt to understand the origins of space and time themselves. Not just understanding the physics of particles, but the physics of the stage on which, and particles and fields, but the stage on which everything takes place in physics. Space and, although we haven't been quite successful so far on that front, time as well. And so familiar words are going to pop up. Entropies, compression. It's an information theory group, so some of you may be familiar with the Slepian-Wolf theorem, distributed compression, all of those things, streaming compression, all of these things are going to play a role in what happens over the next hour. And it from qubit was mentioned in the very kind introduction, and the origin of that term is actually that it's a little manifesto articulated by John Wheeler, who was a very important figure in physics in the 20th century. He was Richard Feynman's supervisor. He was Hugh Everett's supervisor, who articulated the many worlds interpretation of quantum mechanics. He himself either coined or was the person to at least popularize the phrase black hole, participated in the Manhattan Project, and he was a charismatic and important figure in 20th century physics. And he said the following: "It from bit symbolizes the idea that every item of the physical world has at bottom, a very deep bottom in most instances, an immaterial source and explanation. That which we call reality arises in the last analysis from the posing of yes or no questions and the registering of equipment invoked responses. In short, that all things physical are information theoretic in origin, and that this is a participatory universe." So he said this around 1990, or at least it was published in 1990, he first said it a couple of years before. And at the time, or he was ahead of his time. We didn't have the tools yet to really make sense, to make progress on the questions he was really interested in using information theoretic methods. And I think he wasn't even, his intuition was great. His emphasis on measurements and outcomes, I think, might have been a little bit off. What has happened in the intervening 30 years was the development of quantum information theory, thinking intrinsically about the stuff of quantum mechanics from an information theoretic perspective, and not just the classical measurement outcomes and the reality that we experience in our everyday lives. And so in order to talk about quantum information theory, we have to first just agree on some minimal properties of quantum mechanics to make some progress. So first, here's a laser, and there's a slit. And we can ask what happens if we shine the laser at the slit, and I'm sure most of you have seen this before. It goes through the slit. And if we look at where light illuminates some screen in the distance, there's a peak in the middle, and there's some very weak peaks further out that I haven't really drawn here. It's a sine theta over theta squared function, but it basically looks something like this. If you narrow the slit, then the width of this peak broadens, and in the limit of an infinitely thin slit, you get an infinite width peak. Now, if we introduce two slits, of course, the wavefront can hit both slits, with little waves coming out from each slit, and those won't interfere with each other. There's constructive and destructive interference, and so we get multiple peaks in the screen. And so this is familiar wave behavior, nothing terribly surprising. But in the quantum mechanical context, we could say, all right, well, a laser is a quantum mechanical object. The light being emitted is ultimately composed of individual photons. And so what happens with an individual photon in this process? If we just turn down the intensity of the laser, eventually, at any given time, there's only likely to be one photon present. And of course, that one photon, it seems, well, it could take the upper path through the upper slit. It could take the lower path through the lower slit. And if we do the measurements, what we see is a pattern of photons appearing at this screen, if we put some photodetectors, that in which the frequencies reflect the intensity pattern that we saw for the laser, which was just a bunch of photons with the rate at which photons are hitting the slit increased. So this is as it should be. It's not surprising until you think about the fact that in order to generate that interference pattern, you needed the particle to pass through both slits, right? That a particle passing through one slit is not going to interfere with anything. That the source of the multiple peaks is interference. And there's only one particle that requires the single particle to be at two places at once. And this is one of the fundamental signature features of quantum mechanics, that it allows and in fact requires what we would have thought of as mutually exclusive situations to coexist, to be present at the same time. In this case, the mutually exclusive situations being a single particle going one way or going the other way. So information essentials. Let's translate that into bit terms. What is a bit? It's a two-state system. We label the two states 0 and 1. So in the quantum mechanical setting, we can label two states as 0 and 1. So the particle passing through, in this case the photon passing through the upper slit, we could call that 0. Passing through the lower slit, we can call that 1. And quantum mechanics allows both of those to occur at the same time. And in fact, mathematically it's modeled as a linear combination of the two possibilities. Now, it may not be as, because we're familiar with the interference interference phenomena in optics, the fact that this happens for photons may not be terribly surprising. But one of my favorite experiments happening right here on Stanford campus in an adjacent building, the Varian building, is an experiment that looks just like this, but instead of using photons, it uses atoms. And this experiment takes an individual atom, separates on the order, that atom into two locations on the order of 50 centimeters apart, and then brings it back together again to interfere with itself. And it's a very, very sensitive probe of various forces. And so this is really the way things are. This principle of superposition, where multiple incompatible classical realities can coexist, applies to essentially all the states of quantum mechanics. And so you're probably familiar with, from your undergraduate degrees or your high school, with the model of the atom. So here I'd have say a hydrogen atom, and we could call the lowest energy state of that atom a 0. The first excited state, we could call it a 1. And if you supply the right amount of energy, then you can create states that are intermediate in some sense between 0 and 1. But these are not states in which the electron is halfway between the 0 orbit and the 1 orbit. These are states in which there's some amplitude, some coefficient associated with the 0 orbit and some amplitude associated with the 1 orbit, and those coexist with nothing in between. And this is actually one model. We're not going to be talking too much about quantum computers, but one approach to quantum computing is just to use a bunch of atoms. And the electronic states of the atoms represent the zeros and ones. So other kinds of qubits that people use to try to build quantum computers, quantum dots. And so here there's a microfabricated structure in which there's a potential well, or something like this. And so the electron prefers to be in one location or the other, whether it's on the left or the right, is the 0 or the 1. Some of the most popular platforms for developing quantum computers these days involve superconducting circuits, and again, various degrees of freedom that are classically distinguishable are 0 and 1, and we can have them occur at the same time. In some cases, the current flowing one way is a 0, the current flowing the other way is a 1. Sometimes it's the presence or absence of a charge, and sometimes it's things that are a little bit harder to explain. So once we have realized that we can use these microscopic or even macroscopic quantum mechanical objects to represent bits, we can use composites of such systems to describe multiple bits. Right? And so if I have two atoms, I can prepare both of those atoms in the ground state, in the 0 state, so I can think of that as 0, 0. I could prepare one of them. I've labeled them here A and B, A on the left, B on the right. If one is in the excited state, that's a 0, 1. We have a 1, 0 and a 1, 1. And so with two atoms, these two pairs of two states give us 4 bits. And again, that's all fine. And now let's focus on a certain pair of them. So my 0, 1, and my 1, 0. I'm just going to color the 1, 0 example green. And so I have two configurations of pairs of atoms here. In the yellow configuration, the A atom is in the ground state, the 0, and the B atom is in the 1. And in the 1, 0 configuration, it's the opposite. And I've labeled them yellow and green. This principle of superposition applies here as well. And so we can prepare states that are simultaneously either 0, 1 or 1, 0. And so this is an intrinsic form of quantum mechanical correlation, because we know that only one of the atoms is excited, but we don't know which one. And this is different than classical correlation, where we could say, well, there's a pair of light switches and one of them is up and the other is down. Because the reality of the situation is that even if we don't know which one is up and which one is down, one of them has been chosen in advance. It's only our ignorance of the situation that requires us to represent it probabilistically. In the quantum mechanical situation, this form of correlation really embodies the simultaneous existence of both possibilities. And that might sound a little bit like gobbledygook. You know, how can you distinguish between this form of quantum mechanical correlation and the more familiar form of probabilistic correlation? And in fact, for the first 30 years, or for at least 30 years, this was thought to be just a philosophical debate, a very famous debate between Bohr and Einstein that went on for decades. They thought that they were just discussing, you know, they had different views on whether quantum mechanics was a complete description of nature. And they thought that they were discussing a philosophical question that couldn't be resolved scientifically. It turns out there are experiments that can show us that the form of correlation that I just described quantum mechanically is qualitatively different and more powerful than classical correlation. And I'd like to illustrate it for you with a little game. So I have two parties, Alice and Bob. And let's imagine that Alice and Bob are locked in dark rooms with thick walls and no windows and no telephones. And so they're isolated from the rest of the world. And there's a referee. And he looks up at the sky and he sees, you know, he asks, you know, he figures out what the weather is. And he tells Alice whether it's rainy or sunny, and he tells Bob whether it's hot or cold. Okay? And now Alice is going to output a bit, and Bob is going to also output a bit. And we want them to achieve a somewhat strange condition here. We want their bit values to be different if and only if it's both hot and sunny. Okay? So this seems like a contrived game, but I hope that you can stick with me, because it's going to have a profound and important consequence. So the goal is to output, each output a bit. Those bits should be different if and only if it's both hot and sunny. So let's think of a possible strategy for our Alice and Bob. So Alice is outputting green here, and Bob is outputting, I guess it's purple. So maybe Alice, if it's sunny, outputs a 1, and if it's rainy, she outputs a 0. And Bob, if it's hot, he outputs a 0, and if it's cold, he outputs a 1. Does this work? Well, the outputs are different if it's both hot and sunny. That's great. They're the same if, in this case, the same in this case. They're supposed to be the same. They're also supposed to be the same if it's cold and rainy. So they failed. You know, they got one of them wrong. And if you think about this for a moment, it is impossible for them to get it always right. Because if they're to get it all right, then the total number of ones in this table should be odd. But each of Alice's responses appears twice, and each of Bob's responses appears twice. So there's going to be an even number of ones. And so it's impossible for them to get it all right. And so I gave you a strategy that, assuming each of the 4 possibilities is equally likely, will succeed with probability 75%. In fact, an even simpler strategy is they just ignore their inputs and always output 0. Right? Then they're right every time, except when it's hot and sunny. Now, the interesting thing is that, well, the basic point is the only way for them to succeed at this task would be for them to communicate, or for them to be able to look up into the sky and see that it's hot and sunny, or cold and rainy, or whatever it is. But they're not allowed to do that. Or maybe if there's such a thing as telepathy, but we'll ignore such possibilities. But now, let's give them access to a single pair of atoms. that is entangled is prepared in that superposition state that I described before. One of the atoms is in the 1 state, the other is in the 0 state, but we don't know which. Right? So there's an equal weighting for both from the quantum mechanical perspective. It turns out that if they have access to this pair of atoms, that's all they need, then they can win this game with probability 86%. And so this it's a little bit of a parlor game, but this is a conclusive demonstration that quantum mechanical entanglement is a form of correlation that is stronger than any correlation you could ever generate classically. I should say that even if Alice and Bob share random bits, it doesn't help some random correlated bits. It doesn't help them at all. Because at the end of the day, the shared correlated classical random bit just allows them to randomly choose a deterministic strategy. And all deterministic strategies have to fail at least one site, at one of the 4 possibilities. So quantum mechanical correlation is qualitatively different and more powerful than classical. And the conclusion, this is John Bell, the person who identified that there was a distinction between classical and quantum correlations and proposed this kind of experiment for the first time. So quantum mechanical measurements cannot be simulated classically without communication. And what it means for the laws of physics is that 2 basic properties of laws of physics that are so basic that they're often not even articulated as requirements are incompatible. The first one is locality. Right? Locality is the statement that what I do here right now doesn't have an instantaneous effect at arbitrarily long distances away. If that were not the case, it's hard to imagine how we could even build theories of physics. Right? Everything could affect everything everywhere else at any time. And realism is just the statement that objects have well-defined states before we measure them. Right? And that's so basic that it wasn't even articulated as a principle. But one of those 2 things has to be false. And it's hard to get a more profound insight into the nature of reality than you get from this little simple observation. And so that was all by way of trying to convince you that quantum mechanical entanglement is interesting. And it's going to turn out that it's interesting and relevant to understanding the origins of space and time itself. Oh yes, so it's a slippery concept as well. That it can take many exposures before you really grok exactly what is happening with quantum mechanical entanglement and with these kinds of demonstrations. All right, so I gave you Wheeler's manifesto, it from bit. We've reformulated it as it from qubit. What does that mean? We want to understand how the laws of nature, the it of the world, arise from information theory. So what is the it that we're trying to explain? The it is space-time, and black holes, and particularly the quantum mechanical origins of space-time, black holes are good places to look. Because they somehow, as we'll see, intrinsically require both quantum mechanical and general relativistic descriptions. So here is a black hole, and Bekenstein-Hawking, who I guess both passed away fairly recently, sadly, but after long and productive lives, determined that black holes have associated with them an entropy. And in this audience, we all know what entropy is. Entropy is a measure of uncertainty. Right? Shannon and others have taught us that. It's a wonderful, the formula for black hole entropy is a wonderful formula because, well, it contains all these constants, and the constants come from all the different branches of physics. Right? So there's Boltzmann's constant, so it's telling us there's something statistical mechanical going on. There's the speed of light, special relativity. H bar, there's some quantum mechanics. G, the gravitational constant. And then there's this A, which is area. And so the entropy is proportional to the area of the black hole, specifically the area of the region of no return, the event horizon of the black hole. Now, there's a puzzle associated with this black hole entropy, which is that black holes, which are predictions of Einstein's theory of general relativity, the dynamical theory of space and time, there are theorems in general relativity that tell you that black holes are determined, their structure is determined by a remarkably small number of parameters. Just say their mass, their charge, and their angular momentum. Now, if you think of the entropy associated with this room at the moment. What I might do is I'd say, well, I fix the temperature and the pressure and the volume. And once I've done that, there are a huge number of different configurations for the atoms in the room. And the probability distribution that I assign to those atoms, which has to be consistent with my macroscopic parameters that I fixed, is the log of the Shannon formula for the entropy tells us the entropy associated with this room. But in Einstein's theory of relativity, there's no room for any microscopic description. In fact, there's no room for any characteristics at all. The black hole is just purely characterized by its macroscopic parameters, which tells us actually that there should be some underlying microscopic degrees of freedom that are not being described in general relativity. That the theory is incomplete. And so this is an indication that we have to develop a quantum theory of gravity in which space-time itself is an emergent phenomenon, and there's some underlying microscopic quantum mechanical degrees of freedom that are to be explained. And in fact, this formula for black hole entropy, right down to the constants, has been reproduced by the leading candidate for a theory of quantum gravity, string theory. Now, why was Wheeler thinking about these questions? Well, he was aware of the need for quantum mechanical theory of gravity, but it was made very acute also by Hawking along the way when he was working at this formula for the entropy of the black hole. And he realized there was an issue with the dynamics of black holes. And it came up very briefly earlier, black hole evaporation. So imagine that there's some configuration of matter. And you have very precisely specified that configuration in advance. You know exactly what it is. But it has the characteristics of matter that it's going to gravitate, and it's going to move, it's going to come together, and there's going to be enough of it that it's actually going to collapse into a black hole. So you get a black hole in a known state. So there's no entropy attached to that black hole. What Hawking found when he tried to combine general relativity and quantum mechanics is that black holes, which are supposed to be these objects such that if you fall in, nothing ever comes out, they're not as black as we thought. They actually evaporate a little bit. Or they evaporate, just very slowly. And we call that Hawking radiation. So I depict it pictorially, schematically here. Particles come out of the black hole, mostly photons, and they're gravitational analogs, gravitons. And that radiation carries energy, which means that the mass of the black hole has to decrease as a function of time, and eventually it evaporates away, and there's nothing left. Now, general relativity describes the geometry of space-time, and the most basic feature of that geometry is its causal structure. Which points in space-time can influence which other points in space-time? Which points in space-time, in order to travel between them, when you have to travel faster than the speed of light to get between. This is called the causal structure. So that's the most basic property. And the causal structure of a black hole geometry tells you that nothing inside, no information inside, can ever get out. And what that means is that in his calculation, the state of this radiation could not in any way remember what fell into the black hole. And in fact, it turns out that when you study it a bit more carefully, a black hole ends up being a generator of entropy out of nothing. Like, of real, honest-to-goodness, pure randomness just appearing in a microscopically irreversible way. Now, quantum mechanics, the other great theory of physics. You have probably heard or worked with the Schrödinger equation at some point in your lives. And if you took an undergraduate class in quantum mechanics or just read a popular book, it probably wasn't phrased this way. But the Schrödinger equation, which is the basic equation of quantum mechanics, properly understood, says nothing more than that information is not destroyed. That is the Schrödinger equation. And so the fact that Hawking's calculation, where he tried to bring together general relativity and quantum mechanics, led to this conclusion, tells us that the two fundamental theories of physics are in fundamental conflict with each other. That their most basic principles, the causal structure predicted by general relativity and the microscopic irreversibility, which is at the core of quantum mechanics, are incompatible. And so something has to give, and this is why Wheeler was concerned. And he felt that we didn't understand quantum mechanics well enough, and once we did really understand it from an information theoretic perspective, we could resolve these questions. Again, I said he was ahead of his time. He inspired, he had, as I said, he was a charismatic lecturer and scientist, and he had a circle of young people around him who were really very remarkable, who were inspired by these ideas. They wanted to attack the questions of quantum gravity. They didn't quite know how. Among those people was Bill Wooders. You might have heard of the no-cloning theorem of quantum mechanics, quantum teleportation. He's responsible for both of those. David Deutsch, who really first identified the first problems that could be solved efficiently on a quantum computer. Ben Schumacher, who coined the term qubit and who developed the theory of quantum mechanical compression, among other things, and the capacity of quantum channels to send classical bits. All these people were in his orbit. And so while Wheeler wasn't meaning to set off a revolution, which is the revolution that we're now kind of experiencing in terms of the development of quantum information and quantum computing, he did that inadvertently. But now, 30 years later, his vision is coming to fruition. And so this black hole evaporation problem, which was one of the problems that was motivating him, it was vexing enough that back in 1997, Stephen Hawking, Kip Thorne, and John Preskill made a bet about what the answer would be, whereas Stephen Hawking and Kip Thorne firmly believed that information swallowed by a black hole is forever hidden from the outside universe and can never be revealed even as the black hole evaporates and completely disappears, and whereas John Preskill firmly believes the opposite. There's a bet. The loser will reward the winner with an encyclopedia of the winner's choice from which information can be recovered at will. And I believe in 2005, this happened. There is John Preskill triumphantly hoisting the baseball encyclopedia above his head that Stephen Hawking supplied because Stephen Hawking decided that he finally conceded the bet and said he was wrong. Kip Thorne, to this day, has not conceded the bet. He thinks it's still open. But what happened in the intervening years to convince us that we understood what was happening with black holes and evaporation? And what happened is that a sufficiently well-defined, tractable theory of quantum gravity appeared that we could pose the question and answer it. And this is Maldaceno's anti-de Sitter space conformal field theory correspondence. This is a giant mouthful, but I'll just, you don't need to know very much about it, just the qualitative picture. So we need a theory of quantum gravity. And again, anyone in the room who's ever tried to solve some partial differential equations or other problems in physics will know that it's often convenient to put the whole problem in a box, right? And then let the box get big if necessary, but putting the problem in a box makes various things finite that would otherwise be infinite. And so it makes it simpler. And so anti-de Sitter space is like a nice box for quantum gravity. It's very hard to put quantum gravity into a regular box, so it's a special box for quantum gravity. And so it's not like our universe because the boundary conditions are different. Right? We don't live in a box, but this is a box. It's a funny box in that the boundaries of the box are infinitely far away, but it's curved such that if I shine my laser pointer towards that boundary and wait, the signal will travel out to the boundary and come back to me in finite time, even though the boundary is far away. Because time is advancing at a differential rate as you move up towards the boundary. And so here's a picture of it, a depiction. Time is the vertical direction, and the soup inside the soup can is is where quantum gravity is supposed to happen. So quantum gravity is whatever it involves strings and other stuff, exotic things, and the remarkable feature. The conjecture, which has been borne out by many calculations on both sides, is that this theory of quantum gravity, which is really hairy, because it's a theory about the stage on which physics actually takes place, right, is equivalent to another theory, which is basically just the theory of an exotic material which is living on the boundary. Okay, so you just take some exotic material, the kind of thing they might build in a lab here. You make in this picture, the boundary has one spatial dimension. In the real picture, it would have 3 spatial dimensions, but let's just say there's 1. And for the rest of the talk, I'll just pretend there's 1, because that's what the pictures look like. And the bulk quantum gravity theory, in this picture, has 1 dimension more. Right? And so you can study the standard quantum mechanics without any gravity of this this ring of exotic material, and it tells you the full quantum gravity of the interior space. And so gravity emerges, it sort of comes out of nowhere in addition, one dimension of space emerges, right? That in the boundary, this picture, the boundary is a ring, and then there's the vertical direction for time. In the interior, there's two spatial dimensions. That radial dimension somehow emerges in the theory. So space, yeah, comes out of nowhere. And so it's a perennial question, although there's a lot of evidence for this conjecture. How are the bulk degrees of freedom encoded on the boundary? We say that the boundary is a hologram, right? Because a hologram allows you to encode a three-dimensional image into a two-dimensional film. So here you have the three-dimensional space, three dimensions of our space would be encoded into two dimensions of real space. In this case, two dimensions of space are encoded into one. And so there's the perennial question, how do you decode the hologram? And how are the bulk degrees of freedom encoded into the boundary degrees of freedom? And we'll try to say a little bit about that. Now, the spatial slices of this space, right? So the can is space-time, so a spatial slice is a slice of the can. What is the geometry? It's curved, and it looks something like this Escher print. And so the distance between 2 points is the minimum number of fish that you need to pass through to get from point A to point B. And as you can see, the fish gets smaller and smaller as you get out towards the boundary. In fact, there's an infinite number of fish before you go to the boundary. It's negatively curved. And the boundary condition is just that the space look like this as you get out towards the boundary, but you're allowed to put whatever you want inside. You can put stars and black holes and other stuff. And so this gives you a way to study how they behave. So I said the shortest distance between 2 points are you pass through these fish. These are what we call the geodesics in this space. The equivalent, the curved space equivalents of straight lines. The insertion of a black hole will bend the geodesics, and so instead of being these curves right here, maybe it would look something like this if I put a black hole inside. One of the things we've learned from this ADS-CFT correspondence is the importance of the connection between entanglement and space. And I'd just like to show you in an example how that plays out. And so here is a particular a depiction of a particular geometry, space-time, that can occur in this correspondence. So a black hole space-time can look something like this. Now this is called the Penrose diagram. We bend space in various ways, but it's useful for understanding the causal structure. And so I've suppressed some of the spatial dimensions. So I have one spatial dimension and one time dimension. So you can think of it being a sphere at every point. But everything is bent such that light rays always have to travel at 45 degrees. And so this arrow here traveling at 45 degrees corresponds to somebody pointing a laser pointer out towards the boundary. The other arrow corresponds to somebody pointing the laser pointer in towards the black hole. And anything traveling slower than the speed of light will have to propagate between those inside that beam, inside what's called the light beam. And so you see here, a beam of light can make it out to the boundary, which is this vertical direction. So that is outside the black hole. Oops. But if I move the V inwards, the line up top is the singularity of the black hole, point of infinite curvature. And every signal sent from inside this area is going to have to hit singularity. And so this region depicts the interior of the black hole. This particular space-time, however, has a funny feature that there's an exterior here, there's a black hole interior, and then there's this region. And what is that? Well, there's another boundary. There's another exterior. So it's a black hole with two exteriors. And how should we think about that? Well, it's a black hole whose interior is shared between two outsides. This is otherwise known as a non-traversable wormhole, right? So if somebody is on the left, they can allow themselves to fall into the black hole. If somebody's on the right, they can fall into the black hole. They might meet in the middle and say hi, but there's no way for anybody to travel through the wormhole and come out the other side because it's a black hole. All right, so this is a non-traversable wormhole. And we can work out the quantum mechanics of this thing. The quantum mechanical state associated with this wormhole is a big sum, a lot like the entangled state of the pair of atoms that I was talking about. A big sum of states on the left and states on the right, each of which looks like a black hole with only one exterior. So this state here would be some kind of black hole on the left. This one here is a black hole on the right. You entangle them in just the right way, and the interior becomes shared, and there's a wormhole connecting the left and right sides. And so this is a clue that space is stitched together by quantum mechanical entanglement. This is a hypothesis, right? That what space actually is particular configurations of entanglement that organize correlations in certain ways, and that's all space is. It's just entanglement organized in a particular way. Now, is that actually true? To some extent, well, I think the answer is probably not quite. But it's partially true, and we can learn a lot by taking that perspective. To make progress, it's useful, and in fact necessary, to understand how we talk about entropy in quantum mechanics. So this is an information theory talk, so it's about time we discussed entropy. And so let's get back to the entangled state of a pair of atoms. Remember, there was the yellow configuration, which was left in the 0, right in the 1. And there's the green configuration, I should call them A and B. A in the 1 and B in the 0. So let's imagine that we measured the first atom. Right? So we look at it and we say, is it in the ground state or the first excited state? What's going to happen? Well, there's sort of an equal weighting of 0 and 1. So you're going to get 0 probability half, 1 probability half. What if we measure the pair? We look at them both. Well, we're never going to see both of them in the ground state. We're never going to see both of them in the excited state. We're always going to see one excited, one ground. So we get a 0, 1 with probability half and a 1, 0 probability half. Now, measurement in quantum mechanics is an interesting thing. So when I said measure, I implicitly meant measure which energy level the atom is in. But in fact, in quantum mechanics, you have freedom to measure in different ways. And the states form some vector space, in fact, an inner product space. And every orthogonal basis of that space defines a valid measurement. And so I could write down a different orthogonal basis. In this case, the 0, 0 plus 1, 1, 0, 0 minus 1, 1, 0, 1 minus 1, 0, 0, 1 plus 1, 0. And the actual state of the pair of atoms is one of those four possibilities with certainty. And so if I performed this measurement on the pair of atoms, what the measurement would tell me is that, well, you prepared 0, 1 plus 1, 0. All right? None of the other possibilities is present. And so this particular measurement gives me certainty in its outcome instead of uncertainty. Now, Shannon, I think this is, it's a different portrait of Shannon than the one that you displayed at the beginning of the lecture. I thought when you showed yours, I thought everyone always shows the same portrait of Shannon. I thought I was going to the same one, but he's younger than mine. In any case, Shannon gave us this formula for the entropy, minus the sum of probability log probability. And so let's check out what are the entropies associated with these different measurements. Well, for the first bit, for the first measurement, clearly two possibilities equally likely, 1 bit of entropy. Likewise for the second, two possibilities equally likely, 1 bit of entropy. One possibility, 100% likely, there's no entropy there at all. Now von Neumann, in 1929, wrote down a formula for entropy in quantum mechanics. And what that formula amounts to is that you take the minimum over measurement bases of the Shannon entropy. Okay? And that means that it turns out that regardless of what basis you choose for measuring a single atom, you're always going to get 50-50. So the entropy for the A system will always be 1, or is 1. But we found a particular measurement for the pair that has no uncertainty at all, 0 entropy. And so the entropy associated with the pair is 0. And before I go anywhere, I should point out that, and many of you have probably heard this story before, von Neumann ran into Shannon, probably in 1947 or something. And Shannon told him about his theory of communication. So there's this function, minus some p log p, that plays an important role. And von Neumann said, oh, you should call that entropy. of course, because he defined it 20 years earlier. And he also said, because nobody understands entropy, so they'll be particularly impressed by what we do. I guess these days we feel that we do understand entropy much better than they did back in 1947. Now, okay, so we've calculated two entropies. Big deal. But you're information theorists, and you should see something bizarre about these two entropies. If you have two random variables, x and y, and you calculate the entropy of x and y, what do you know about the entropy of x and y compared to the entropy of x? Anyone? Right. You are always more uncertain about the whole than the parts in information theory, right? Again, let's think about the hot, cold versus sunny, rainy. I am more uncertain about the pair of random variables than I am about either one individually, right? Obviously. And entropy reflects that by an inequality. The entropy of AB should be bigger than the entropy of A alone. Quantum mechanically, that fails. The entropy of the whole can be less than the entropy of the parts. You can be more certain. In fact, in this case, we are completely certain about the whole while being completely uncertain about each of the parts. And this isn't a bug, this is a feature. This is a reflection of the fact that quantum mechanical entanglement, and this is an entangled state, is a form of correlation much stronger than anything you can achieve classically. Classically, the best you could do is a 0. Quantum mechanically, you get a -1. And there's an operational interpretation attached to this that we'll come to later. Now let's discuss, so we know a little bit about what entropy is in quantum mechanics. Let's talk a little bit about how it behaves in ADS-CFT. So, with the two atoms, I labeled one atom A, the other one B. More generally, I could say there's some subsystem, some collection of degrees of freedom I call A, and some others that I call B. So here, I have my ring of material from my ADS-CFT correspondence, the ring of exotic material that's around the outside, whose physics is supposed to encode quantum gravity. And I take a piece of it and I call it A. Von Neumann said, minimize over all measurements the entropy of the measurement that you would get, and that will give you the formula for the entropy. That sounds like a tall order to calculate here. Some exotic material strongly interacting, blah, 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 blah. So, turns out there's a simple formula for this entropy in this correspondence. And the formula tells us that we can evaluate the entropy by a geometrical quantity, right? So this is an example of how this correspondence works. Some quantum mechanical question in the boundary theory that doesn't involve gravity gets translated into a geometric question. Geometry is Einstein's relativity. And entropy is supposed to be the minimal area of something. So there's some family of curves, and you calculate the minimal area. The curves you consider, in this case, my region is a line segment. Basically, it's line segments that are anchored on the ends of A. And you find the one of shortest length, so that's the geodesic, the one that passes through the minimum number of fish. Its length, up to constants, gives you the entropy. This actually generalizes the formula for black hole entropy to a large class of regions, and in particular, empty space. We now have a way to associate entropy to empty space, which gives us a count of how many microscopic degrees of freedom there should be in empty space. What is the interpretation of this? I want to give you a kind of operational nuts and bolts compression interpretation. So the entropy of this region A, let's imagine that some Alice holds this material in her laboratory. Right? There's no quantum gravity or anything else. She has this. She has access to this material A in her laboratory, so it's a lot of degrees of freedom. So you can think of it as a lot of quantum mechanical random variables. And there's an entropy associated to it. As information theorists, you would say, well, what does the entropy count? It counts the minimal number of bits required to compress that down, the minimal number of bits that would be required to send the information associated with that data. And there's a quantum mechanical theorem that says the exact same thing is true in quantum mechanics. The minimal number of qubits that would be required to send the quantum information of this region is controlled by the entropy. And so the minimal number of qubits required to send the information associated with that region A is the length of a curve, and it's the length of the shortest curve in some family. That's interesting, right? Because the the compression protocol that is most efficient, that uses the fewest resources, corresponds to the shortest curve, right? You're minimizing two things. Maybe they're the same thing, right? So we could ask, what is the length of some arbitrary curve, which is not the shortest length curve, in this space? Can we figure out what that is? And now we're getting really nuts and bolts. There's going to be an analogy to streaming compression. So let's talk a little bit about streaming compression. Netflix. Okay, so if Netflix was going to send you a movie, right, the best possible compression that they could supply to you would be to compress the whole movie at once, use all the correlations present in the movie, and that will give you the shortest, the best compression. And in physics language, this would exploit both what we call the UV correlation, the short time correlations. Like for example, here's some stills from the movie Interstellar. The scene doesn't change that much from still to still, so you can only send the changes, so that's UV correlation. But there's also IR correlation, infrared, long distance correlation, or long time. So the star of the movie is Matthew McConaughey. His facial expressions might change, but still the same face from still to still. The best possible compression algorithm would make use of that fact. In streaming compression, generally, you restrict your ability to take advantage of the long distance correlations, but you do exploit the short distance correlations over some window. So that's actually going to be how we interpret the length of an arbitrary curve in this geometry. Here, I was talking about a ring before, and my A region was some subset of that ring. Let's just let the radius of the ring get really, 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 really big so it becomes a straight line. Okay, so my boundary, this is my segment of the boundaries, this straight line here, and my curve in the bulk is this, this hump shape. I'm interested in interpreting the length of that hump. Now I do something kind of odd and interesting. I don't know if you find it interesting or not. To each point on the curve, I construct its tangent geodesic, right? So in flat space, to every point on a curve, there's a tangent line. In curved space, there's a tangent geodesic. And the tangent geodesics in this depiction are actually circles, so they're going to intersect the boundary at 2 points. So for each point on my curve, I have a tangent circle, and that intersects the boundary at 2 points, and then that defines a line interval, which is the interval between the two ends of that circle. So here are my line intervals. I have little circles corresponding to small intervals, large circle, large interval, and so on. And now I imagine that Alice, again, wants to send the quantum information contents of that region to Bob. But we're going to constrain what Alice and Bob have access to in their compression protocol. They don't have the full infrared, the full long distance access. They can only access a finite window at every step. And it's a sequence of windows given by these intervals. And so there's a correspondence between curves and collections of intervals, and a collection of intervals defines a streaming compression protocol. So they compress, and the theorem is that the length of the convex curve, or the length of the curve, is the minimal qubit cost for Alice to transfer the subtended portion of the boundary state to Bob in a streaming compression procedure with curve-dependent locality and scale constraints. Whew. So basically the answer is, the optimal qubit cost of this protocol, the best way that you can accomplish this streaming protocol with these restrictions, the cost is going to be the length of the curve. And it was, I think this was a useful advance because it gives us some indication of how the points inside the bulk further away are related to points on the boundary. Right? The deeper into the bulk you go, the bigger the circle, the larger the subtended portion of the boundary is. So that the more IR, the more long distance the correlations are related, the more long distance correlations are related to the deeper points inside the bulk. Because, well, maybe I will mention this a little bit. The way that one proves this kind of thing is that you take this curve here, and you write the length of the curve as the sum of a bunch of infinitesimal portions. And the infinitesimal portions can be built out of portions of these circles. And the length of one of those circles is an entropy of an interval, because the circle is one of these geodesics. And so you get a formula that looks like some integral, really, an infinite sum, over all the intervals you're talking about. of the entropy of some interval minus the entropy of that interval intersected with the one before. Now, again, it's an information theory discussion. This is the entropy of something minus the entropy of part of that something. It's a conditional entropy. Right? So it's a big sum of conditional entropies. And as we saw earlier, conditional entropies in quantum mechanics can be negative. Right? And so wait, what does that mean? Right? So I said that the minimal qubit cost is the sum of these conditional entropies. The conditional entropies can be negative. What's going on, right? Like, how can you have a negative cost for a compression protocol?
So I'll quit this.
Yeah.
So I think I seem to be missing something there. You know, we're looking at one of the intersections of the next previous interval, right?
Yeah.
What prevents us from having intersections of more than one interval?
So that's just the rule. So I've just defined that rule. Like in principle, right? So I think what you're saying is Alice, you know, if she has a hard drive or something, you know, quantum hard drive, she could make use of everything she received previously, in principle, right? So that doesn't give the right answer in this case. It's important that she has sort of a finite memory. And so there we deviate from a practical question about streaming, where you really might just say, okay, well, I have unlimited local storage, and I'm just going to store the whole thing, although that might be unrealistic, right? It's kind of realistic to assume maybe you have some finite budget of cache, you're going to use that.
Right.
But the size of your cache varies as a function of time when you're performing this compression protocol. Sometimes it's small and sometimes it's large. And whether the cache is big or small depends on the shape of the curve that defines your compression protocol. Okay. Yep. Okay. So what is this negative uncertainty? What is negative conditional entropy? And this is really one of my science writers. Sometimes they get it right, sometimes they get it wrong. Sometimes there's too much hype. Sometimes they're confused. But sometimes they just nail the headline. So this is my friend Andreas Winter. He and his co-authors provided an operational interpretation of this negative conditional entropy in quantum mechanics. And the basic story is that the cost to send something defined by A, some degrees of freedom, from Alice to Bob, and Bob already has B, is the conditional entropy of A given B. Entropy of AB minus entropy of B. So those of you who've taken an information theory course, again, I mentioned the Slepian-Wolf theorem. This looks exactly like the Slepian-Wolf theorem. There are two random variables, x and y, and you sample from x and y. Alice has x, Bob has y already. How much additional information does Alice have to send Bob so that he can recover x, the conditional entropy of x given y? So this is a slightly different formulation, involves sending qubits and so on, but very, very similar. When this number is negative, it turns out that the procedure costs no qubits at all. And moreover, the procedure gives you something useful at the end. You manage to get out some high-quality entanglement that you can use to reduce the cost of future procedures. And so, there's no mystery to what a negative cost is. It's a profit. Right? That when you try to compress, it doesn't cost you anything at all, and you actually make something useful out of it. All right, so moving on a little bit, the goal in this enterprise is to see whether we can derive geometry from quantum mechanics, right? Derive geometry from information theory. And to one extent, there's a sense in which, or some very interesting steps along that direction have already been taken. I'm going to talk about somebody else's work here. So this quantum mechanical formula for entropy that I told you about, minimize all measurements, there's an operator rho associated with a quantum state. So instead of minimizing all measurements, you can formulate things as minus the trace of rho log rho. Rho is some matrix. So it looks like p log p. The trace is like a sum. This is a general quantum mechanical formula for entropy. Quantum mechanics also has a relative entropy. The Kullback-Leibler divergence. And you just do the same thing. Where you had a sum, you put in a trace. Where you had a probability distribution, you put in an operator. And then, I guess that's the whole story. Right? So trace of rho log rho minus rho log sigma. As you know, relative entropy is non-negative, and it's equal to 0 if and only if the probability distributions are the same. Same with quantum relative entropy. It's greater than or equal to 0, and it's equal to 0 if and only if the quantum states are the same. Now, this inequality, we can choose our states rho and sigma. to be two states that are very close to each other, and just expand this to first order. And so we're expanding it around, this function around its minimum. So the linear term is 0, right? Which means that to linear order, this inequality is an equation. So we just use the fact that relative entropy is non-negative, and we get some kind of equation. And in that equation, on the left-hand side is a change in entropy. And on the right-hand side, it turns out is a change in something that can be interpreted as an energy. Now, what I've been telling you throughout this talk is that entropy is proportional to area, right? So it's geometry. So this is an equation that says geometry is equal to energy. This should be an equation. You may not know Einstein's general relativity, but that is the spirit of Einstein's general relativity. It's an equation that says geometry is equal to energy. And we call this the first law of entanglement entropy. If you take that little equation, which is trivial to derive, in the boundary theory, in the theory of this exotic material, and then you apply it to all boundary spheres, so in this picture, to all intervals, and you also allow yourself to change reference frames in the boundary. So you look at reference frames that are moving at a constant speed, right? So the inertial reference frames of special relativity. So you combine that data, and from that, you can actually derive Einstein's equation, at least to linear order and more recently to second order. And so what this means is that Einstein's equation, which is the equation that tells you what geometry does, and where it comes from, you can derive it from the information theoretic properties of this boundary theory. Right? That's where it comes from. Gravity emerges from information theory. There's still work to be done along these lines, but that's the objective. I said we should be able to it from qubit. It's actually happening. So hopefully that was not totally incomprehensible. I tried to give you a sense of what quantum mechanics, the basic features of quantum mechanics that are interesting from an information theoretic perspective. Superposition and entanglement are the two key features. It's an information theory meeting, so we talked about entropy and the properties of quantum mechanical entropy, and then saw how understanding quantum mechanical entropy can give us insight into the theory of quantum gravity and even into the origin of geometry itself. So there's a lot of work to be done in this area, but it's exciting. And with that, thank you for coming this evening, and I'm happy to take any questions.
Maybe I'll stick in one to start with. So I guess if I understood things correctly, I mean, like you talk about string theory, you're talking about equations, about that being a solution for quantum gravity. I mean, would it be fair to say that you're also working towards this unifying quantum mechanics and relativity? Is that right?
That's definitely the case. That the old picture, I would say, is that what people would do is, given some classical system like a harmonic oscillator, they say, well, how do I quantize the harmonic oscillator, right? Like, how do I write down a quantum system that is kind of the limit of the harmonic oscillator as the quantities become very small and microscopic? And so people try to do the same thing for gravity, right? The degree of freedom in gravity is basically what's called the metric, how you calculate distances. And they try to quantize Einstein's theory of the metric. And you get something, but it doesn't seem to actually be the right theory of quantum gravity. What quantum gravity really is some statistical, or what gravity is, space and time, are some averaged effect, just like temperature and pressure are averaged effects, right? And microscopically, it's something different. And so what we're trying to do is see how gravity emerges from non-gravity stuff. And so the theory of this exotic material, there was no gravity in it, and we see gravity emerge and a direction of space emerge. So it's an emergent phenomenon when you look at a quantum system in certain regimes. And that's our best understanding right now.
So information is more fundamental than either space or gravity, is that what I'm hearing?
Yeah. Well, so I'll put it this way. So there's a trivial sense in which this has to be true, right? Like, so what is space and what is time, right? So what is space? What does it mean for this point to be close, for these 2 points to be close together? It somehow means that there's a lot of correlation between what's going on here and what's going on there, right? That's really what space is. right? That it's a way of organizing the correlations that we observe in the world, right? And so what is information theory? Information theory is also a particular way of organizing and quantifying the correlations that we see in the world. And so to the extent that space is an emergent phenomenon of something microscopic, the fact that information theory gives you nice functions and quantities to evaluate correlations, mutual informations and conditional entropies and so on, it's not really a surprise that they come out in this effective theory. And likewise, I mean, it's for the same reason that entropy plays a role in statistical mechanics, right? I'm always puzzled, like some people strenuously object. They say, oh no, Shannon's entropy and thermodynamic entropy are not the same thing. They are exactly the same thing, right? Thermodynamic entropy is just describing our ignorance of the underlying microscopic degrees of freedom that are present. And it turns out that in the theory of statistical mechanics and physics, entropy plays a major role. And it played a major role even before we knew about the microscopic underpinnings and information theory. And so it's, again, should not be a surprise that because gravity is an emergent statistical theory, that information theory should be important. And I think it's even more important than in standard statistical mechanics. Like some recent developments that I didn't mention here. This quantity relative entropy. Relative entropy can be shown to basically be equal to what's called canonical energy in general relativity. That these things are very, very closely related to each other. And so it emerges, so space and time, space and time are ways of organizing correlations. Information theory is a way of talking about correlations that is particularly well motivated and works well. Yeah.
Well, nice. So one other quick question. I think that you mentioned string theory, but just incidentally.
Right.
And so it always seemed like there are different methods of unifying quantum mechanics and relativity. And string theory is one of the major ones, right? People have these problems with it. But it almost seems like you're not using string theory.
Yeah,
I'm
well,
just kind of curious what's the story there. So
it's a very good question. So most of what I said, interestingly, can be agnostic about whether string theory is correct. So what I'm talking about right now is the semi-classical limit of quantum gravity, right? That there is actually an underlying geometry to talk about, right? Like the really, really quantum strange stuff of quantum gravity is when there's no geometry left to talk about. And so in the limit where the geometry becomes very classical, strings are of less importance. And so in this ADS-CFT correspondence, there are different examples. Some of them look stringy, some of them look like other things. But the kind of arguments that I've been giving here applies to all of them. Now, if you really are, ultimately you have to understand the microscopic theory of quantum gravity, and then the details will differ. But the kind of arguments I've been making here are actually very robust. And so I think that they will survive whatever the underlying theory happens to be. The caveat is that, as I said at the beginning, this is being done for these spacetimes that are asymptotically anti-de Sitter for the most part, right? These spacetimes that are in a box or in a can, and that's not our universe. And so there's an assumption that the underlying physics does not radically change by imposing these boundary conditions, right? That the theory of quantum gravity of our universe is different, right? Our universe is expanding, it doesn't seem to have any boundary. And so if that radically changes the story, then whatever I've said here could be wrong. But the reason to think it shouldn't change it that radically is just that we're allowed to put whatever we want inside anti-de Sitter space, right? And so while in the limit it has to become regular and have this boundary, in some localized region, it can be doing whatever you want and it can look a lot like our world. And so I feel like the lessons we learn here should be transferable, but it's an open question. Yeah.
Can you tell us a bit more about how we can achieve the 86% for the toy example?
Sorry, how we can...
So you said you we can do 75% if we don't have any correlation. Like Alice and Bob are not talking for the deterministic strategy, but then if we have some quantum correlation, we can do better. We can do 86%.
Oh, how it's done?
Like, yeah, some intuition, or is it too complicated?
Well, I can describe how it's done. So Alice gets one particle, Bob gets another particle. And actually, instead of talking about two atoms, let's think about two photons, and let's think of the qubit as the polarization of the photon, so the angle at which the wave is waving. And that actually corresponds to the measurements that are mostly done in the real world in any case. So when Alice hears sunny or rainy, she decides whether to measure in this basis or that basis. And when Bob hears hot or cold, he decides whether to measure in this basis or that basis. So there are four different bases, and how they are aligned depends on the particular combination of questions that is asked. And the geometry of that alignment and the correlations that are induced when you perform the measurements leads to this 86%. It's the cosine squared of pi by 8. So there's a little bit of geometry to be done, but that's like the procedure is very simple. Alice performs a measurement based on what she receives, Bob performs a measurement what he receives, and they just output the results. That's the whole story. Yeah?
You mentioned towards the beginning, I think you said that a certain perspective you could take is that space and time might arise from entanglement, and then you said that's probably not true, but it could be useful to take that perspective.
Right.
I'm wondering about the other side of that. Like, why is that? Why do you think that's probably not true?
So the reason I think it's probably not true is, so we spoke a little bit about these, so one reason, about this geometry where you had a black hole with two exteriors. You had two exteriors that two geometries that both had a black hole, but the interior of the black hole was shared between them. So you can construct very similar geometries where that wormhole becomes very, 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 very long. And then the entanglement type quantities that you can calculate from this boundary theory, right? From because you still have the left and the right side, so you can calculate various entropies. Like let's say we just calculate entropies at the both sides. Those involve geodesics, right? And you can reach a point where there will be no minimal length, there will be regions of the space-time where no minimal length geodesics pass. And if no minimal length geodesics enter some region of the space-time, then none of the entropies have any information about the geometry there. And that happens. So because of that, there has to be more to it than just the entropy. But you could say, okay, well maybe it's not just entropy, maybe I should look at a Renyi entropy, right? Or do something, so there are other probes of that type, and it could be that if you just extend the notion a little bit, beyond Shannon type entropies to other types, that might be all the information you need. Lenny Susskind's response is that you have to go beyond entanglement to talk about complexity, right? And there are reasons to think that might be the right thing to do. But at the very least, we know for a fact that just considering entropies can't be the whole story. These entropies are these boundaries.
Wanted to know more about your the experiment with the single atom that you mentioned at the beginning. Some 5 years ago, I saw a demo at the Photonics in San Francisco. Is it the same or it's a different? It could be the same. That is the reason I mentioned that one. But I want to understand your experiment, the setup, and what are the observations you are making. Is it an ongoing thing or it is done? And
So this is just the double slit experiment?
yeah, that you
You
talked
have this,
about.
you're doing this experiment over in the variant.
Basically,
Oh, sorry, that variant. I'm not doing that experiment, I should say. This is Mark Kasevich and Jason Hogan. So I'm a theorist, not as useful a human as those experimentalists. Yeah, so that experiment, what it is, there's a 10-meter tall tower dug into the basement of the Varian building, and there's an atomic fountain at the base. So it actually produces a Bose-Einstein condensate, so it actually is many atoms at once, but conceptually you could think of it sending up a single atom. And So an atom comes up, or is launched upwards, and then a laser beam is shone on the atom. And if the atom absorbs the photon, the atom gets a momentum kick. And if it doesn't absorb, it doesn't get the momentum kick. And so you end up with the atom being a superposition of absorb, not absorb. And so if it gets the momentum kick, it starts moving away. Otherwise, it goes up. And then another laser, so it gets to the top. Another laser at the top then does the reverse. So they start coming back together again. Jason Hogan and Peter Graham, who's a theorist, again, in the physics building, they have a proposal to use this idea to build a gravity wave detector. So I don't know if you've heard about LIGO. This experiment, I mean, really one of the most phenomenal experimental stories and inspirational stories ever. So they detected gravity waves for the first time a couple of years ago using these two detectors. They're interferometers. They're about 1.5 miles, the arms of the interferometer. And the sensitivity is that a gravity wave goes by and it shifts the length of one of the arms relative to the other by an amount smaller than, like, what is that? But much smaller than the size of a nucleus of an atom. Much, much smaller. And the experiment is sensitive enough to detect this. So that experiment is sensitive in a frequency range, which is interesting. It's quite low frequencies. Well, I think like maybe 1,000 hertz and lower. Right. So when the news came out, you could actually listen to. They detected two black holes orbiting around with each other and then collapsing into one another, and they were orbiting at about 400 hertz. So it's in the audible range. So you could listen to the black holes orbiting each other and then merging. So this atom interferometry experiment, the proposal is to put up a satellite or a pair of satellites, and that would be sensitive at a higher frequency range, which would then allow you to detect these objects long before they actually collapse, and then tell all the telescopes in the world, look over there, there's going to be something spectacular, there's going to be a black hole merger, or neutron stars, or whatever it is. So that kind of experiment, I mean, it's amazing that it can be done, just like it demonstrates quantum mechanics, but it actually has potential applications in terms of very extreme sensitivity measurements of very small forces. Is that helpful? Or, yeah.
So I'm curious about the interaction of negative entropy with positive entropy, and what happens, because in nature, for instance, we do witness increased organization, for instance, in biology or cell biology, or where life basically creates more organization and more cohesion over multiple generations. So what happened, and what are the actual metrics of where these equations start applying? What quantities of dimensions or measures?
All right. So this kind of negative entropy it's hard to imagine biological systems taking advantage of this, because quantum mechanical conditional entropy can be negative only if there is entanglement in the quantum state. And if you have I haven't spoken about the formalism that you use to talk about probabilistic mixtures of quantum states, but the kind of states that you will actually encounter in biology most of the time, or in classical information theory, just don't allow this possibility of negative conditional entropy. Now, there are specific cases, like biological molecules, where it is hypothesized that quantum mechanically coherent effects are important, like in photosynthesis, for example. And I've never looked at it, but I suspect that if you went and looked at that system, you might be able to find that the degrees of freedom, some of them, entered states of negative conditional entropy. there's another little caveat to this, or not a caveat, but another part of this story about how negative conditional entropy can manifest itself in, let's call it the real world. So one of the connections between information theory and computation, or maybe let's say information theory and, well, one of the connections is that, or you could ask, what are the minimal information theoretic constraints on computation, or statistical mechanical constraints? If you want to erase a bit, right, meaning that the bit is in some state and you want to set the state to 0, right? There was some uncertainty there. The microscopic laws of physics, classically or quantum mechanically, are reversible. So you have to take that entropy and put it somewhere. And we generally put it in the environment, and that means that you're pumping heat to the environment. And so there's something called Landauer's law that says if you want to erase a bit, you have to release an amount of energy, kT log 2, an amount of heat. You have to dissipate kT log 2 heat. Now, there's a quantum mechanical addendum to that story, which is that if you have a computer and you want to erase a bit in the computer, but the computer has a memory, and you're allowed to access the other qubits of its memory, with the only constraint being that you erase the bit that you want, you set the other bits have to remain in the state they started in, then the cost of erasure is kT, conditional entropy of your bit given the rest of the computer. I mean, that's the same classically. It's kT times the conditional entropy. But classically, that conditional entropy is always non-negative. Quantum mechanically, it can be negative, which means that quantum mechanically, erasing a bit doesn't necessarily have to dissipate heat. It can actually be battery. Right? You can get energy out of it. And so again, maybe there is some biological molecule that takes advantage of this fact. At the moment, I think the only people who have, it's only been studied as an abstract phenomenon.
Okay, if possible, we'll go for one more question. Does that work for you guys?
So there are 2 hands. Read 2 hands and then...
Okay, 2 questions then.
The last one's... Yeah.
Oh, you want me to go? Okay.
Yeah, go ahead.
So what's wrong with considering negative entropy as time going backwards?
So the entropy itself doesn't know anything about time. It is about an instantaneous state. The story of time reversal and quantum mechanics and entanglement is a very interesting one. That if you have from a mathematical perspective, if you have a quantum state and you want to know, is it entangled? Then you can play the game of time reversing one half of the state. And if it's entangled, if it's not entangled, that's going to give you something reasonable. If it is entangled, you get something broken often. And this is called the partial transpose test, and it's used mathematically a lot to study entanglement. So time reversal and entanglement and entropy-like quantities appear that way. But negative entropy, I think, is a different phenomenon. Yeah.
Again, about negative entropy, you said like it's like some kind of credit for applying to subsequent. The question is, can be applied to different processes. So is it an entropy universal, a scalar variable, or maybe multidimensional, some kind of?
Yeah, that's a great question, actually. And so I didn't talk about how this procedure was really formulated, because it would have complicated things a little bit. But this compression procedure, what you do...
Would you mind repeating the
Okay, sorry. So repeating the question, I think the question was saying that when you have this negative cost for this compression, that can be viewed as a credit that can be used in the future. But there are many different kinds of things that you can do, and potentially there could be many different kinds of credit. And so the fact that this is just a single number, what does that mean? Like, do you get some kind of universal resource out of it? And the answer is you do get a very universal resource. And actually what you get out of it, what the number counts, the basic entangled state that we were talking about, 0, 1 plus 1, 0, it counts how many of those you get. And so if you want to, we didn't discuss something called quantum teleportation, but if you want to send a qubit from one location to another, if you have one of those entangled states between the two locations, then you can get by with that entangled state and talking on the phone. So an entangled state upgrades classical communication into qubit communication. And so it tells you how many qubits you can communicate. And that kind, we call it a bell pair. That bell pair is useful for a phenomenal number of different tasks. Like it really can substitute for communication. It can be used to distill secret key. You can, like there are a lot of different things you can do with it. And so I'd say it's really quite a universal resource. And in the context, like you can define the entire task in terms of how much how much entanglement between Alice and Bob is consumed or produced. And there is a single number that given an arbitrary quantum state, you can say this is how many bell pairs are required to make the state and how many bell pairs I can get out. And asymptotically, those are the same number. So that there's really like the issues of having many different incomparable resources or anything like that is not a concern here. It's a concern in many other circumstances, but not here.